Continuing with our work on volumes of revolution, in the last set of videos we talked about our cross sections of our three-dimensional solids that were formed by taking our area in the plane and swinging it around a horizontal and vertical line. Having that done was a three-dimensional volume of revolution, and the cross sections of that were little cylinders. And so we're going to see what happens when we don't have a nice beautiful region in the plane that's right next to the line that we are spinning about. As you can see here, we have a region that's bounded by these two functions. The line y equals 2x is the upper bound, and the parabola y equals x squared is the lower bound of the area in the plane. And so what we're going to do now is we are going to swing that around as near as I can the x-axis. And so usually what I start by doing is just drawing a mirror image of the region on the other side, just reflecting the region over the line that we're spinning about. So this says we're revolved around the x-axis and to find the volume. So the first thing I'm going to do is just draw a reflection of it, and then I'm going to try, let's see if I can do this here, to draw what taking that region around that line, that center line, draw what that might look like. And as you can see here, if I go from the line on top to the line after the reflection from this point and swing it around in a circular fashion, including that point, and then back around here, I have again, from this center point, I have a disc. You see that disc? Do you see that cylinder? Just like we had before in the last lesson. This is what we've got going on, and there's the center point. And so again, I have a cylinder. Now, let me pick a different color. And there's something different about this cylinder. It's not all of this region in the plane that's being swung around or revolved around this horizontal axis here. Only what's being revolved around there is this region, this area. So there's actually a hole right here in the middle of this. Do you see that? There's this big hole in the middle of our disk here, and that hole, if I give it some thickness, is going to look like that. And then this is supposed to be the center. I didn't do a good job drawing, but from the center point up to the edge of the inner hole there is another cylinder. It's smaller, but it's coming out of the center of our whole disk. So we have this whole disk, and in the middle of it is this smaller disk that has some thickness to it, like so. And here's its radius from the center to the lower function, the bottom bounding function, versus this radius coming from the center to the upper bounding function. So hopefully you can see what's going on there. And I also hope that you see now, instead of having a cylinder or a disc, we have a washer. That's why this is called the washer method, because this looks like a washer. It is a cylinder with a hole in the middle. Now let's talk about what the hole versus what's going on there in the center. Let's go back here. I'll pick up my red again. I want to make sure you can follow what I'm doing here. And in order to differentiate what's going on for the hole, the big one, the red one, versus the green one, I'm going to call this radius big R, and then I'm going to call this radius here little r. All right, so if I was to find the area of the base of this cylinder, that, again, just like in the last lesson, is the area of a circle. That's pi r squared. And then I'm going to find the height of my cylinder, or for us in this context, you've heard me call it the thickness. It's easier to kind of determine that we're talking about thickness when we turn it on its side here. But that's with respect to x for this particular example that we're using. So if I wanted to find the volume of this disk, it would be pi r squared dx. And let me fix that. Pi big R squared. Said I was going to call it big R and then didn't. So let's figure out what big R is. According to what's going on here, big R is the distance from our line to the x-axis. Well, the distance from the line to the x-axis is just this function here, 2x. So R equals 2x. Now, I'm going to pick up my green and we're going to talk about what the volume of this center disk, this hole in the middle that gives us a washer, that, again, still the area of the base. Now it is pi little r squared, and it's still the thickness. This still has thickness along the horizontal axis right there. That will be dx. So for us, the distance in the plane trapped in between the parabola, y equals x squared, and the x-axis is going to be little r. So for us, little r is the parabola. Now let's see what we can do about finding the volume of the solid that's actually going to come about from this revolution. Hopefully I can draw it. It's going to look like this on the outside because the line is in charge on the outside. But on the inside, and I'll draw it kind of in broken, on the inside, it's pretty much going to look like this after we get through revolving things around. So this is what our solid would look like. There's the center of everything. That would be big R, and here's still the center here. If we stop there on the inside, that would be little r. So hopefully you can kind of see what our three-dimensional solid would look like. And what we want to do is we want to start at this x value, we'll call it A, and we want to stop at this x value, we'll call it B, and we want to add infinitely many of those washers together. So now we have to determine what is each washer going to look like. And our washers are going to be the area of the whole big thing taking the area of the little disk in the middle out of it. So here is the volume. I said area when, volume is going to be when I bring thicknesses here. But if I take the volume of this big whole disk and I subtract from that the volume of the hole in the middle, that's actually giving me the washer, because this is really truly what a cross-section in this context looks like. It's a washer, right? And so if I just want the volume of this thing, it's the volume of the whole thing taking the volume of the hole in the middle. So basically what this would look like is here is the volume of the disk, large disk, minus the volume of the hole in the center, right? So both of these have a pi in them, so if I factored that pi out front, it would begin to look something like this. So you can see how important it is that I identify the radius of the whole thing and then the radius of the hole in the middle. This is W-H-O-L-E and this is H-O-L-E, right? All right, so I'm going to pop my pi out front, and I have pi big R squared minus pi, because remember that's going to distribute through, little r squared. So there would be the volume, and I still have to figure out what A is, and I still have to figure out what B is. Haven't done my limits of integration yet, but I have found what the volume of this three-dimensional solid will be, because it's going to have a hole in the center of it, right? It's going to be hollow in the center. All right, so let's figure out what our limits of integration are. Let me see if I can clean this up a little bit, get some of this out of the way. I think you get the general idea. So let's figure out what the limits of integration are. Because here, and this is unlike last time, they're not actually just overtly given to us. So this is going to be the left endpoint of our interval over which we are integrating, and this is going to be the right endpoint. Just like we always know, or just like we intuitively remember about A and B. Well, we can clearly see here that it looks like A should equal 0, but it's a little harder to see. It looks like B should equal 2, but we can't be certain. So we understand that this point and this point, whatever it is along the axis, comes from the intersection of these two functions. So just like our first lesson this spring that was area of a region in the plane bounded by two functions, the upper bounding function and the lower bounding function, sometimes the region in the plane, lots of times actually, the limits of integration came from their intersection points. So not always, but sometimes we're going to find these values from intersection points of the graphs or of the functions. So where 2x equals x squared. Now, remember your algebra, ladies and gentlemen. This is how we solve something like this. All right, so I'm going to factor an x out. That leaves me an x minus 2. Each one of these factors, either x equals 0 or x minus 2 equals 0. Don't forget algebra just because we're doing calculus. So it does turn out that the left intersection point is 0, the right intersection point is 2. So those are our limits of integration. So we're going to integrate. I think I'm just going to clear all of this off, and that may help us. So we said we were at pi. We're going to integrate from 0 to 2. We said big R was 2x, the upper bound is the line. We said little r was x squared, the lower bound is the parabola. And there we have it. There is, using the washer method, which means we're going to have a hole in the middle of our cylinders. So we need to subtract that volume from the entire volume of the disk. Here's how we're going to find it. So I'm going to pop my pi out front. Let's clean this up. This is 4x squared. Hopefully you see that. And this is x to the 4th. So I'm going to have 4/3 x cubed minus 1/5 x to the 5th. And I'm evaluating that from 0 to 2. So my pi goes out front. I have 4/3 2 cubed minus 1/5 2 to the 5th. There's the first part of fundamental theorem. The last part, everything has an x in it, and it's not an x plus anything. So the last part of fundamental theorem, evaluating at the lower limit, will just go to 0. And at this point of the game, of the calculus that we're doing, as long as you're absolutely certain that is what's going on here, it's okay just to write the 0 there. So I have pi times 2 cubed is 8. 8 times 4 hopefully is 32, so that's 32/3. And 2 to the 5th is 16/32. I'm not going to go ahead and try to put those together and do the algebra. You get the general idea there. So this is the volume of the three-dimensional solid that was found by revolving the area given about the x-axis. So pretty cool. If we revolve the area, the region in the plane, around an axis or a line, and it has a hole in the middle of it, we're not using the disk method, we're going to use the washer method. I have more examples to do, so look for the next video.